Moving on, let's look at the solutions in alternative form. Well, knowing these various relationships, we can rewrite the free response equation for an underdamped system as this. And this is what you may have seen before, okay? So notice the only change we've made is we've replaced minus gamma upon 2 with minus zeta omega naught, okay? Because that's the relationship we came up with. And so that's the form of the equation you may have seen before, okay? So zeta omega naught gives you the extent to which the thing is decaying, okay? And obviously omega d and alpha are the same, and a is the same. And we'll talk a little bit about how you apply initial conditions for this equation in a minute. For an overdamped system, again, if you look at the equation that we came up for an overdamped system, you can make the substitutions and you get this form of the equation. Again, it's 2 decaying exponentials. Okay. And then we had a critically damped system that looked a bit like this. Okay, again, it's a decaying exponential. But this is the difference between a system like this and a system like this. This is the fastest way to get to 0 without overshooting. That's the idea behind critical damping. Here you'll get to 0 eventually, but depending on the various terms, it'll take longer. And obviously an underdamped system will overshoot, but depending on your damping ratio, it'll either overshoot a lot or it'll overshoot not very much at all. Okay. Most systems in nature and in engineering will have a little, they'll be underdamped to an extent. Okay. Now for force damped equations, okay, if you remember we came up with an equation that had A and delta in, and A, instead of being defined by initial conditions, was defined by the characteristics of the system. Now we had an equation for A. It looks a little bit like this, but it didn't look quite like this. But one of the exercises in your notes will be to find this equation from the other equation in the one that we covered last week. But you can rewrite it in this form, okay, in terms of omega naughts and in terms of zeta, okay, and obviously wherever you see an omega divided by omega naught, okay, you can substitute in R. Can anybody spot the small mistake in this slide? There should be, right here, another 2, because omega naught is squared as well. Okay, so you can make that change in the notes if you want to. This is on page 29, where it says slide 54. And for phase angle delta, you can do the same thing. You can substitute in wherever we had a zeta, you can substitute in, where we have a gamma, we can substitute in the new form in terms of zeta. And again, down here, you can change that around, and you end up with this equation in terms of R. Now last week we also had this equation. If you remember, if we go back to that slide with the pictures on, this one here, the value for this amplitude when you're at this frequency is defined by Q times by the static amplitude. So here we've got a Q of about 5. Okay. Static the amplitude ratio here is 1. You multiply that by Q, you get up to there. Okay, so increasing Q, you get a bigger peak. And obviously we came up with an equation that relates Q and damping ratio. And so you can basically replace Q with 1 upon 2 zeta. And you can see quite clearly that as this goes down, if zeta is small, then the amplitude will go up, and vice versa. So it's just taking the equations that we covered last week and putting them in alternative forms in terms of zeta and things like that. And again, we covered this briefly. The frequency that results in the maximum amplitude is defined there, 1 omega naught square root of 1 minus 2 zeta squared. Okay, and the amplitude at maximum frequency is f naught upon k times by this term. Now that's, like I said, this bit is the addition that we've got you know, the previous slide we had 1 upon 2 zeta, okay? But obviously this bit here accounts for the fact that it's not actually at the natural frequency, it's slightly less than, depending on how much damping you've got. If we go back to that picture again, you can see that as the damping increases, the peak is at, first off at R equals 1, okay, but as the damping ratio, as the damping increases, okay, you can see that the peak is moving slightly less than, okay, so that doesn't actually occur at omega naught. Okay, now to go on, I do say lastly up here, but there's some bits more after this. This is the form of the equation. Most of the equations that we came up with had a similar form to this. Okay, sometimes there was an exponential in there. Okay, and the phase might not be written as phi, but just as an example, this equation can be written like this. It's a sinusoid, that equation. Okay, with a certain starting point talked about by phi. Okay, and this equation, this one down here, can also be a sinusoid. Okay, now we've obviously got a cosine and a sine in here, but obviously you can still have that being called a sinusoid. And to get from one to the other, it's quite straightforward. If you know the trigonometric sum and difference identities, we know that if you've got cosine of u plus v, you end up with cosine of v minus sine of u, sine of v. Okay, and likewise, vice versa, if you've got a minus in that quantity there. Okay, and you end up with a plus over here. And so we had cosine of omega t plus phi. Okay, so you can plug in that equation. So I've taken this equation here and I've used this equation here and this result over here. You end up with a cosine omega t cosine of phi minus sine omega t sine of phi. And what we do is we define a1 to be a cosine of phi and a2 to be minus a sine of phi. And so you can plug that into this equation, plug these two things into this equation, and you end up getting a cosine of omega t plus phi is equal to a1 cosine of omega t plus a2 sine of omega t. So that's an alternative form for that equation. This here is an alternative form for this equation here. Okay. So you may see solutions written like this, or you may see solutions written like this. And in the next chapter, we're going to be using this as our solution, not that. Okay, but they're the same thing, knowing that you've got A1 and A2 are defined like this. And so, the solution for the free undamped response, okay, so this is the basic form, can be written like this, where A1 is a cosine of phi and A2 is minus a sine of phi. Similarly, for the damped response, we had this form of equation, okay? So now we've got the exponential in here, the decaying exponential. In terms of zeta, we can write that as a1 cosine of omega dt plus a2 sine of omega dt multiplied by that decaying exponential, because that decaying exponential affects the sinusoid. Okay, as time increases, that will reduce the amplitude and affects the amplitude of the sinusoid. And obviously, for that equation to work, a1 must be a cosine of alpha, and a2 must be minus a sine of alpha. Now we're going to use these equations to come up with some cunning equations that you can use. If you know the initial conditions, you can jump straight to the solution. So for the free undamped equation, remember I talked about in the tutorial, when you've got initial conditions, what you need to do is you need to apply the displacement when time is 0, and you need to find the derivative of the equation with respect to time, to find x dot, and then if you know the velocity when time equals 0, you can use that equation again as well. And that will allow you to find a and any phase, phi or alpha, depending on which equation you're using. So here we've got the undamped case, so that up here, the first equation you see is that's the solution, the general solution, where we know neither a nor phi. But if you apply the initial condition at time equals 0, okay, which I'm going to call x subscript 0 over here, you can see quite clearly that what you end up with is a cosine. That term is 0, so you end up with a cosine phi. Okay. And here, if you take the derivative of this equation, obviously you get an omega naught that comes out, and the cosine turns into a minus sign. So you end up with a minus a omega naught sine of omega naught t plus phi. Plug in 0 for t in here, you end up with minus a omega naught sine of phi over here. So that's x dot subscript 0. And we also know that the solution is a1 cosine omega naught t plus a2 sine omega naught t. That's what we just covered. And if you remember, a1 is a cosine of phi. Well, that's quite clearly x naught. So there's your initial displacement, okay, at time equals 0 is a1. And a2 we know is minus a sine of phi. Well, here we've got a minus a sine of phi. If we divide that by omega naught, then that's your x. Then that's your a1, a2, and obviously there's our initial condition in terms of velocity. So if you've been given a question that's a free, undamped system, and you've been given initial conditions of what happens when x is 0 and what happens when x dot is 0, sorry, when time is 0 for the displacement x naught and the displacement x dot naught, then you can go straight to that solution, this one here, okay? Knowing that x naught is a1 and a2 is x dot naught divided by omega naught. And so there's the solution in terms of initial conditions. So like I said, if you know your system is undamped and it's free oscillating and you've been given x naught and x dot naught, you can go straight to the solution, which is on your equation sheet, you'll see, and you'll have your solution. You don't need to worry about having to make the derivative. Okay, and like I said, that's on your equation sheet, which is at the back of your book. Now we can do a similar thing with the damped response. If you remember, the equation up there was our damped response. So it's very similar to the the undamped response, except we have the decaying exponential in here. Okay? And if you plug in 0 for t, then obviously e to the power of 0 is 1, so that disappears. This term drops to 0, and so you end up with a cosine of alpha, which is equal to x subscript naught. Okay? Now, this is where it gets a bit more complicated. X dot of t, if you take the derivative of this equation, okay, you have to use both the product rule, because you've got two functions of time in here, this one and this one. Okay? So you have to use the product rule. And you have to use the chain rule with both of those terms as well. Okay, so when you take the derivative of e to the minus zeta omega naught t, you end up with e to the minus zeta omega naught t times by minus zeta omega naught. Okay, and obviously when you take the derivative of cosine of omega dt, you end up with minus omega dt times by sine of omega dt. Okay, now because you've got the product rule in here, that's why you've got both of those terms in here. Okay. If the screen was working with the pen, I would explain it in more detail, but it's quite, obviously it's not. But if you came to the tutorial, I would have covered it as well. So if you plug in 0 for the derivative, for the velocity, okay, you end up getting, obviously this term drops to 1. You retain a, you get minus zeta omega naught times by cosine of alpha. Now cosine of alpha quite clearly is x naught, okay? A cosine of alpha is x naught, so you know what those two terms are, and you get minus omega d sine of alpha. Okay. Now we know that x naught is a cosine of alpha. We can rewrite the velocity equation at t equals 0 as this. Okay. And it's quite clear that you can rearrange to find minus a sine of alpha, okay, as this term. So there's our A1 for that alternative form, and there's our A2. So you can take that term and plug them into the alternative form that we had. So there's the alternative form. We know A1 and A2, and so you can plug them in and you end up with this equation here. Again, this is on your equation sheet. So if you've got a free damped system, like question 5, which we'll do again using this form in a minute, okay, you end up with, you can jump straight to it, because if you know the initial conditions, here and here, okay, you can work out what zeta is, and omega naught and omega d, you can just plug the numbers in and you get the same solution as you got when you did question 5 before.